In this video, we're going to take a look at the definite integral and express it as a Riemann sum. So we suppose f is continuous on a to b. So of course, when we draw a nice little graph of this, what we're saying is that it is continuous between point A and point B. We divide f into n subintervals with a width of delta x, which of course is the total distance between the 2 points divided by the amount of subintervals. We've seen this before. So we have a bunch of intervals here. And what we do is we say that the definite integral from a to b of f of x dx is equal to the limit as n goes to infinity of the sum of I through n of f of xi star times delta x. Now, if you watched the previous video, you know that this is about dividing a curve into a bunch of different rectangles and then taking the area of the rectangles. And what we're doing is as we go to infinity, we make the rectangles infinitely small, which gives a very nice approximation of the area underneath the curve. Now, what's new from the last video is this xi star notation. What we're saying is that if we have an interval from xi to xi plus 1, then xi star just can lie anywhere within the subinterval. So it doesn't matter where xi star is anywhere in the interval, because it'll give you the same result, and that is all we're saying here. So this is the definite integral. We'll show you how to use this in the final slide to actually compute an integral. But for now, we need to do some terminology here. This on the left here, this squiggly s, is the integral sign. What we have here, we have a, which is going to be a lower limit. So this is the leftmost point on a graph if you're in Cartesian coordinates. We have b, which is the upper limit. Basically, you go from a to b when you integrate. So a is going to be x0 and b is going to be xn. Our f of x here, this is the integrand. So this is the function in which we are integrating. And over here on the right side, this sum right here has a special name called the Riemann sum. And this is basically the sum of all the rectangles. So that's all the terminology. Of course, when I say integrate a function from a to b, it should be fairly obvious what I mean. I'm taking the area underneath the curve. And this limit is a nice way to compute it. But before we compute the limits, I just want to show you guys some general results of what we do here with integrals. So if our function is always increasing, then our integral, or the area, is always going to be greater than 0. So what this means here is on a graph, if our function is always greater than 0, then clearly the area here is going to be greater than 0. On the other hand, if our function is going to be, say, less than 0, then if we evaluate it where the function is less than 0, then the area is going to be negative. Now, yes, we can have negative area in integrals. In fact, the result of an integral is the signed area of a region, which is basically the area above 0 minus the area below 0. So, say I have a nice little curve here that goes like this, and we take 3 separate areas, A1, A2, and this will come down and be A3 here. So essentially, we take the area throughout these 3 regions. Our area is just going to be A1 plus A2 plus A3, where a2 is going to be a negative number. So yes, you can have a negative area when it comes to taking definite integrals. Kind of interesting, and you might say, what are the applications? Well, what this really means is that your area is underneath the curve. In some cases, this means that you are left or down if you're taking a three-dimensional plane or something like that, and you'll see some applications a little bit later. But these are just some general things that I hopefully are like pretty obvious. If a function is positive, then clearly the area underneath the function will be positive. Now, I do want to, of course, take some limits, but I've introduced sums, and I haven't really introduced how to write them out, or how we sum all these numbers in an efficient manner, and what we can do with things. So here's some formulas that you just need to memorize. If we sum a bunch of numbers from 1 to n, so this is 1 plus 2 plus 3 all the way to plus n, this can be computed with the formula n times n plus 1 over 2. If you want to prove these things, discrete math course, mathematical induction video, that's a great place to go to prove these things. When summing the squares of numbers, this is, for instance, taking 1 plus 4 plus 9 plus 16 all the way up to n squared. The formula is going to be n times n plus 1 times 2n plus 1 all over 6. Now, if we take the numbers 1 through n, and we're just adding the number c, so this is a constant number, this is basically saying c plus c plus c, and we just keep adding c a total of n times. So your result is going to be c times n. Now, a cool thing about taking multiples of numbers when doing sums is that if you have c times a1 plus c times a2 plus c times a3 all the way up to c times an, you can factor out a c, and you can make the computation a little bit easier. So if we have the sum of I equals 1 through n of c times ai, we can rewrite this as c times the sum of I equals 1 to n of ai. So again, this part right here is just this notation, and this part right here is this notation. Now, there's a couple other things that are fairly obvious, I would say. If we take the sum of ai plus or minus bi, this is equal to the sum of I equals 1 to n of ai plus or minus the sum of I equals 1 to n of bi. And if you write this out, so for instance, on the left here you have a1 plus b1 as the first term, and then you add a2 plus b2, and so on and so forth, all the way up to plus an plus bn, you can rearrange them and you'll find something similar that is equal to the right side, which you can write out and prove yourself, but it's pretty useful when breaking things up. So we're going to use these to compute a definite integral. So we have the definite integral from 0 to 2 of x squared minus x dx. This is very complicated the first time you see this, so I'm going to go through this one example, end the video, and then we'll continue on with this lecture in another video, just to give you guys some time to digest it. So let's take the definite integral here of x squared minus x. There's a couple things we need to know. First of all, we should probably write out the formula so we can figure out what we need to know. So we take the limit as n goes to infinity of sigma of I equals 1 to n of f of xi times delta x. Okay, well what we need to know is we need to know delta x. So delta x is b minus a over n. So our b, our upper limit, is 2. Our lower limit is 0, so we divide by n. So this will be 2 over n. Now, what I haven't taught you is how to calculate this xi. But what you might remember from the previous video is that x0 is equal to a, x1 is equal to a plus I times delta x, since we add the interval delta x one time to get to x1. So sorry, this should be plus 1 delta x. To get to x2, we take a and then we add delta x twice to get to the point. So we go all the way up to xn by adding a plus n times delta x. What this means is that the general formula for xi is going to be a plus I times delta x. So for this specific equation, we can just plug in some numbers here. So a is 0, okay, I is going to be I, and then our delta x is going to be 2 over n. So our xi is going to be 2i over n. So this is the value we're going to plug into our equation. So let's do this. Okay. We take the limit as n goes to infinity of the sum of I equals 1 to n of f of xi. So what we do is we plug this 2i over n into our x squared and to our x. So this will be 2i over n squared minus 2i over n, and then we multiply the whole thing by delta x, which is just 2 over n. Okay, well, let's expand the inside a little bit. I'm not going to rewrite the sum while I do this one step, but this is going to be 4i squared over n squared minus 2i over n, and this whole thing is multiplied by 2 over n. So what I'm going to do is I'm going to distribute the 2 over n inside. So this will be 8i squared over n cubed minus 4i over n squared. So now we have the limit as n goes to infinity of the sum of I equals 1 to n of 8i squared over n cubed minus 4i minus n squared. Now what we'll do is we're going to use some of the laws that we saw on the previous page. So we're going to take the limit as n goes to infinity, and now because we're subtracting two different things, let's call this a, let's call this b, we can break the sums up. So we have the sum of I equals 1 to n of 8i cubed, sorry, this should be 8i squared over n cubed, minus the sum of I equals 1 to n of 4i over n squared. Okay, now let's use another law and move the constants from outside of the sums. So we take the limit as n goes to infinity of, now we have 8 over n cubed times sigma from I equals 1 to n of I squared minus 4 over n squared times the sum of I equals 1 to n of I. Now, why do we want to isolate the i's here? Well, we know formulas for this, and if we take the limit as n goes to infinity, we need to have everything in terms of n to cancel things out. So, we have a nice spot right now where we just have the sum of I squared and the sum of I, so we can put the formulas in for these two sums here. So we're going to get the limit as n goes to infinity of 8 over n cubed times well, the sum of I equals 1 to n of I squared is n times n plus 1 times 2n plus 1 over 6. And then we're going to subtract 4 over n squared times the sum of I equals 1 to n of I. The formula for that is n times n plus 1 over 2. So now it's a very simple limit problem. So when we do some expansions, I'm going to use a shortcut here. I'm only going to take the highest power of n in each term. So we're going to get 16n cubed over 6 on this left side. Again, we just take n times 2n, which will be 2n cubed. We multiply that by 8, and that'll be the highest power. And then we have n cubed times 6. And then we will subtract 4n squared over 2n squared. And again, we just distribute n times n, which is n squared. Then we multiply this by 4, so we get 4n squared. And then we have 2 times n squared. So this should be 6n cubed on the bottom. Now, when we take the limit as n goes to infinity, what we're going to get is 16 over 6 minus 2, which will be the same thing as saying 2/3. So we have found the area. It's just 2/3. So of course what you're thinking now is, wow, that was a very long process to find the area underneath a curve. Especially when we have this integral sign that is really just equal to this Riemann sum, so why do we have an integral sign if we just have another formula for it? So of course you probably guessed, hey, there's a faster way. And you would be right, but that is not for this video. In fact, that is going to be for a later video. We still need to do a little bit more with Riemann sum stuff in order to get you guys used to this, because I promise you, I absolutely promise you, no matter where you take your course, no matter what your prof teaches, your midterm number 1 will have a Riemann sum question on it. And you will have to compute an integral using the Riemann sum. I have never seen a first midterm that does not have a question on this. And there's a couple tricky things that they can do with these questions. What they can do is, when computing your xi's, you remember that the formula is a times I times delta x. A plus I times delta x. Now, in the homework, they give you questions from 0 to b of f of x dx, where b is some constant number. But when it comes to the exam, you'll usually have a question that, say, instead of 0 to 2, might look like this question from 1 to 3 of x squared dx. Now, your xi is going to look like 1 plus 2i over n. Because delta x is just 3 minus 1 over n multiplied by I. So instead of the previous question, where it was the same distance and it was 2i over n, you have to add in that first number. So what this does is it makes the algebra trickier. And if you forget the formula, where you have to have the a here, then you're going to get the question wrong. And there is one more tip I have for you that is very difficult for first-year math students, and I highly, highly recommend that you listen to this and you try really hard to follow this advice. In calculus, the questions are algebraic, usually. It's more of applications and how you can solve the questions. But to really learn calculus, especially integral calculus as opposed to just derivatives, which are very conceptually easy, you really should learn the theory for integration. And what I mean is, when I did these graphs of say, these functions that go from a to b, and I explained what was going on here. So you take some triangles here, you have an xi and xi plus 1, and I said, okay, it doesn't matter where xi star is in the interval, it will add up to the same thing. What you should be thinking is, what does that mean? And when I give you the formula to get from a to xi and give you the general formula, which this is a plus I times delta x, you should be able to understand this geometrically and what this means. This means that I'm going I rectangles over, and I'm starting at a point A. So what I'm doing is from the origin, first I'm going A, and then I'm going I times delta x over to get to the rectangle I'm evaluating. So you should really understand the theory. This first stuff really isn't too bad, but later in the course, with integration techniques, with applications, understanding what's going on geometrically with graphs is really going to help a lot more than just learning how to do the questions and just by doing a few examples and trying to figure out the odd trick you need to do. Because if you figure this out with graphs and geometrically, this course becomes very, very easy. If then, and I promise you, this stuff is going to be a lot easier if you learn the theory. So that was the first half of definite integrals. I'm trying to keep these videos under 25 minutes each. So I will continue next time, where we're going to take a limit, express it as an integral, and perhaps we'll do some trickier stuff. And I'll give you a few more rules about definite integrals. So if you have any questions, leave them in the comments below and I will get to them as quickly as I can.